Okay, so there are some physics problems that are very simple and very interesting. The model is so simple and classic, such that those questions won't appear on any sort of exams or tests or competitions, but they are they are worth studying, and uh, and we are going to introduce one of those questions uh, to you in this video. So this is a question about electrostatics. We have a regular tetrahedron, which means that we have uh, right, so which means we have um, all the angles and sides equal and symmetric, uh, right? So this is um, what looks like a regular tetrahedron. So we can see that there are like four faces denoted by one, two, uh, three, and four. Four is the uh, so four is the surface um, bounded by these 3 points, right? And uh, so the question is as follows. So phase one, so we have all all these four faces of this tetrahedron are conductors, and uh, the uh, uh, the size uh, that joins those two faces um, are the size that joins two faces are insulators. So we can have because a conductor is a equipotential surface or body, um, uh, but once two conductors are separated by a insulator, then those two conductors can have different potential. So we have surface one has potential phi one, right? Or use V1, and surface two has potential V2. Surface 3 has potential V3, and surface 4 has potential V4. So each surface of this tetrahedron is a conductor, and between two surfaces, they are joined by insulators along the sides. Okay. Now this tetrahedron has a center, right? So this center O has equal distance to all the surfaces, all the four surfaces, right? And the question is, given the four potentials of the four surfaces of this tetrahedron, then what is the potential uh, of the center O? This question this question is easy once you know the method, and it's hard if you don't. But if you just want to get the answer out, it's very simple, right? Because you can uh, because the four faces are completely symmetrical with regards to the center O. So you can't imagine any other answer than something like v0 is equal to k, which is a constant, times v1 plus v2 plus v3 plus v4, right? Because all the faces are symmetrical with respect to the center, and so imagine if you replace one of the plus by a minus, say v1 minus v2 plus v3 plus v4, then what's special about the second surface? No one knows, and in fact there's nothing special about it. So the problem is just to find that proportionality constant k, and in fact if you assume that v1 equals to v2 equals to v3 equals to v4, then the whole system, the entire tetrahedron, is an equipotential body, right? Therefore, the center O must have the same potential, right? For example, if you have v1, right, that's if v1 equals v2 equals v3 equals v4 equals to v, then VO is also V, right? Because if the whole system is the equipotential body, then the insulator along the sides has completely no use, right? Has complete no use. It the whole system can be regarded as a single conductor, right? And then inside the conductor there cannot be electric field lines because the conductor is an equipotential body, and because there is no electric field lines inside the cavity, right? Inside the cavity of a conductor, the potential is the same as the conductor, right? So because there is no charge in there's no isolated charge inside the cavity, right? So that's that goes back to the high school level physics, right? So that means this K must be 1/4, right? So right, so we have the answer, well, the correct answer is V0 is equal to 1/4 of V1 plus V2 plus V3 plus V4, right? Now we will try to find a way to rigorously prove that this equation holds. How to rigorously prove this? Well, we can use the rotational symmetry of this tetrahedron, right? So if I fix 4 positions A, B, C, and D corresponding to the initial position of faces 1, 2, 3, and 4, then we can rotate the whole system, right? So initially we have 1 corresponds to position A, phase 2 corresponds to position B, and 3 and 4 corresponds to C and D respectively. Now if we fix phase 4 to position D and then rotate A, B, and rotate 1, 2, and 3, then we can have 3, 1, 2, 4, and 1, 3, and 2, 3, 2, 3, 1, 4, right? So those are the cyclic permutations of A, B, C, and 1, 2, 3. And then we also have if we fix, for example, position 1, we have we then have 1, 3, 4, 2 and 1, 4, 2, 3. So 1, 3, 4, 2, and 1, 4, 2, 3. And if we fix phase 2, we have 3, 2, 4, 1 and 4, 2, 1, 3. So it's 3, 2, 4, 1 and 4, 2, 1, 3. And if we fix phase 3, we have 2, 4, 3, 1 and 4, 1, 3, 2. Right? 2, 4, 3, 1 and 4, 1, 3, 2. Corresponding to position A, B, C, and D. So that's how we rotate the tetrahedron. We fix the tetrahedron, one face of the tetrahedron, and rotate the tetrahedron 120 degrees with respect to the line perpendicular to the face that we fix, and that line goes through the center of the face that we fix. So now we can just take 4 combination of this, which are 2, 3, 1, 4, right, and 1, 4, 2, 3. 3, 2, 4, 1, 4, 1, 3, 2. Right, and if you add them up, you will see that and also because of symmetry, the middle point, the center, does not change, right? And because it's the exact same tetrahedron, we just rotated it. The center, the potential at the center is the same. So and also because of the principle of superposition, we can add these 4 tetrahedron up to get a new big tetrahedron, such that on all 4 faces we have potential V face, which is equal to V1 plus V2 plus V3 plus V4, right? See, in phase A we have 2, 1, 3, 4. Phase B 3, 4, 2, 1, right? So we add them up. We now get a new superposed big tetrahedron that has this all the faces have the same potential, V1 plus V2 plus V3 plus V4. And in the center we have simply 4 VO, because we just add the same 4 potential at the center together, right? So and because all the faces have equal potential, the center must have the same potential as the faces, right? Because we can treat the superposed tetrahedron now as an equal potential body, right? So they have to be equal, right? So now we have 4V0 equals to V1 plus V2 plus V3 plus V4, right? We get this formula.